Hello everyone, welcome to Math Cafe. I'm Sulagna, your maths mentor. So today we'll discuss about the concept of differentiability of a function. The continuity chapter has been uploaded and the link is provided in the description box. So today we'll discuss about differentiability. Differentiability at a point. What do you mean by differentiability at a point? Let fx be a real valued function defined on interval ab. Let c belongs to ab. That means c is a point within the interval. So fx is said to be differentiable at x is equal to c if limit of x tends to c, fx minus fc divided by x minus c exists finitely. That means this limit will give us finite value. So what is the LHL and RHL? If this is the limit, LHL equals to limit of fc minus h minus fc divided by c minus h minus c when h tends to 0, or you can say 0 minus. And what is RHL here? Limit of h tends to 0, fc plus h minus fc divided by c plus h minus c. And if both the values are equal, that means limit exists there. If that limit exists, then the function is said to be continuous and differentiable at the point x is equal to c. Here we can cancel c and cc. So it will give us a negative value if this value is positive, and if this is negative, this will give us positive. And if this is positive, here we'll get the same value. Sign will not change. And this left hand limit is also known as left hand derivative, LHD. And this is RHL is also known as RHD, that is right hand derivative. So this is known as derivative, or we can say f dash x. F dash x is equal to limit of x tends to c, fx minus fc divided by x minus c. So LHD is known as f dash x minus, and RHD is known as f dash x plus. So now let's represent it graphically. So this is a geometrical representation of our differentiability. Here I have taken a random curve which is given as y is equal to fx plus c. And P is a random point on that curve. And the coordinates of P is x and fx, because we have taken x in x-axis and in y-axis we have taken its function, that is fx. And Q is another point whose coordinates are x plus h and fx plus h. So this is x and this is x plus h. So what is the slope of PQ? Slope of PQ is equal to y coordinate of Q minus y coordinate of P divided by x coordinate of Q minus x coordinate of P. So this is fx plus h minus fx divided by x plus h minus x. So when h tends to 0, if it will move to this side. When x tends to 0, that means Q point will come closer to P. So if the Q point will come closer to P, then this red line will be like this. So it will represent or it will be a tangent at point P when Q will come nearer to P. So we can say when h tends to 0, the chord becomes the tangent. Limit of h tends to 0, fx plus h minus fx divided by x plus h minus x. That means limit of the slope of PQ. H tends to 0. That means we are moving the point Q nearer to P. So this means limit of h tends to 0, slope of chord PQ. So when h tends to 0, it will become tangent. So this will become slope of tangent at P, which is the limiting position of the chord. That means when Q point will come closer, then we'll get a tangent. And this is equal to f dash x. Limit of the slope of PQ is the derivative or differentiation of the function fx. So we can say that if function fx is differentiable at point P, if there exists a unique tangent at point P, that means there will be only one tangent at point P if the function is differentiable at that point. So what happens in an interval? So differentiability at an interval. A function is said to be differentiable in an open interval AB when it is differentiable at each and every point of the open interval. And what happens in a closed interval? A function is said to be continuous in a closed interval if it is differentiable at every point of the closed interval and it is differentiable from the right at A and from the left at B. So RHL or RHD at A should exist and LHD at B should exist, and each and every point of AB also. So what is the relation between continuity and differentiability? We can say if the function is differentiable at x is equal to c, then it is continuous at x is equal to c. So the first condition for differentiability is the function should be continuous at that point. So for continuity, what is the condition? Limit of fx when x tends to c is equal to fc. So if we will prove this, then we can know that if the function is differentiable at x is equal to c, then it is continuous at x is equal to c. So let take limit of x tends to c, fx minus fc divided by x minus c is equal to f dash c, which we have discussed earlier. So let's write fx as fx minus f of c plus f of c. So the value is same here. Now let's multiply x minus c and divide with this x minus c and plus fc. So by taking limit now in both sides. So this is the condition now, limit of fx, x tends to c is equal to limit of x minus c, fx minus fc, x minus c into x minus c plus fc. So this line is similar to this. I have just written here so that you can understand easily. So now we know limit of fx plus gx is equal to limit of first function plus limit of second function. So it is just a split. And again we know that limit of fx into gx is equal to limit of fx into limit of gx. And limit of fc when x tends to c is equal to fc only, because it is a constant. So now limit of fx minus c divided by x minus c when x tends to c is equal to f dash c. We have considered it here. And what is the value of limit of x minus c when x tends to c? This is 0. So f dash c into 0 plus fc. So what will be the value? The value is fc. So when the function is differentiable, we have taken the function is differentiable. Now we have proved here the function is continuous. So we have proved our point. Hence fx is continuous at x is equal to c when it is differentiable at x is equal to c. So what about the converse of the statement? We have already proved if a function is differentiable at a particular point, then it is continuous at that point. Now let us check if a function is continuous at a point, whether it is differentiable at that point or not. So I have taken a modulus function because we have already proved that modulus function is continuous everywhere. So let us check if it is differentiable at x is equal to 0. So for that we have to find out the left hand limit and the right hand limit. Left hand limit is equal to limit of x tends to 0 minus g of x minus g 0 divided by x minus 0. Here gx is equal to minus x because it is modulus function, and x minus 0, so this is equal to minus 1. So what happens in the case of RHT? RHT is equal to limit of x tends to 0 plus gx minus g0 divided by x minus 0. So here gx is plus x. So x minus 0 divided by x minus 0. This is plus 1. So this is not equals to RHT. So it is not differentiable. Though it is continuous at 0, but it is not differentiable at 0. Or in the graph you can see this is the graph of modulus function. At 0 the graph is very sharp, and at 0 we can draw various tangents. Not one, we can draw various tangents. But for condition of differentiability at the point, it should be unique tangent. That should be a unique tangent. So from the graph also we can say it is not differentiable at x is equal to 0. So let us discuss the conditions of differentiability. The first and most important condition is the function should be continuous at that point. If the function is not continuous at the point, then it is not differentiable at the point. Next condition is the function should not have any sharp corner or vertical line. The graph of the function should not have any sharp corner. You can take example here. If the graph is like this, so it is not continuous. So it is not differentiable at this point. Or the graph is like this. A vertical line is there. So here also it is not differentiable. So now let's solve a problem so that you will be clear with the concepts of differentiability. So fx is a function which is defined as 1 minus x square when x is less than equal to minus 1, and it is 2x plus 2 when x is greater than minus 1. We have to check the differentiability at x is equal to minus 1. So for checking the differentiability, what we have to find out? We have to find out the left hand derivative and the right hand derivative. So let's find out the left hand derivative. LHD is equal to, let's first find out the value of f of minus 1. F of minus 1 is equal to, when x is equal to minus 1, function is defined as 1 minus x square. 1 minus minus 1 square. So this is equal to 0. So LHD equals to limit of x tends to minus 1 minus fx minus f of minus 1, and here x minus of minus 1. So this is equal to limit of x tends to minus 1 minus, in case of fx we can write 1 minus x square minus 0 divided by 1 plus x. So now it is 1 minus x square, 1 plus x. So this is equal to limit of x tends to minus 1 minus 1 minus x, because 1 minus x square is 1 plus x into 1 minus x, and we can cancel 1 plus x from both numerator and denominator. So this is equal to 1 minus of minus 1. This is 2. So 2 is our LHD. So let's find out the RHD now. RHD is equal to limit of x tends to minus 1 plus fx minus f of minus 1 divided by x minus of minus 1. So this is equal to limit of x tends to minus 1 plus fx is 2x plus 2 here, 2x plus 2 minus 0 divided by x plus 1. So by taking 2 common, we'll get x plus 1 here. So it will be limit of x tends to minus 1 plus x plus 1 into 2 divided by x plus 1. So this is 2. So this equals to 2. So our LHD equals to RHD, where at point x is equal to minus 1. This is important. So the function is differentiable at minus 1. So this is all about the concept of differentiability. In the upcoming videos, we'll do more questions based on continuity and differentiability. So I hope the concept is clear. So please like the video and subscribe the channel and press the bell icon so that you will get all the notification. So work hard and keep studying.